Okay, so today I'm going to talk about the development of SmartIR technology, in particular about the adaptive thermal control system that we are developing. We are a space and defense company, but today I'm going to talk mainly about space, but the same technology can also be used for defense application. So the team has been growing quite significantly since the last time I was here. Before we were only 5 people, and now we are 13. And we are making very good progress. So space is an extremely challenging environment, as we know. In particular, like we have extremely temperature fluctuation. There is the vacuum of space, and the only way to transfer the heat is via radiation. Okay, so we had to use radiative cooling. Moreover, satellites are becoming more and more powerful, so meaning that we had to dissipate more heat. We are talking about, for a large satellite, up to 12 kilowatt of power. And in order to prevent the satellite from baking, we have to develop advanced thermal control system, which can control the temperature of the satellite. So developing a thermal control system is not something easy. Of course, we have the sun, so we have to balance out the incoming radiation of the sun. We have the radiation coming from the Earth, but also we have the payload that is, when it's on, is producing power. And then the only way to stop the satellite from baking is to have a radiator that is able to emit the infrared emissivity, infrared radiation. So heaters normally are currently used as a way to balance the temperature of the satellite. So when, for example, the payload is off, or where we are in the dark side of the orbit, the satellite tends to overcool. So we're using heater to heat up and maintain the satellite at the right temperature. But this is quite energy consuming. We can consume up to 40% of the total power of the satellite. So we're talking about 40%, it's quite a lot. And one way that SmartIR is trying to solve this challenge is by creating a tuneable radiator. So meaning a radiator that can be switched on and off on demand. Here just a quick, I don't know if I can. Okay, yes. This is basically the working principle of our technology. We have a device that when it's off is acting as a radiator, so is emitting heat. But then when a small voltage is applied, we can start to suppress the infrared emissivity, and therefore the device looks cold. But actually the temperature didn't change, okay? The only thing that changed is the emissivity of the material, so the optical properties. This is some specification of our radiator. So we are able to tune the infrared emissivity between 0.8 to 0.2, so 0.4 emissivity modulation. In order to have, to save power, have to be low power consumption. So we are talking about 2 watt per meter square. And of course also lightweight, so 100 grams per meter square as well. So extremely light material. We ran some case studies using through our collaboration with Airbus, and we find out that for a satellite of 800 kilo and 1 kilowatt power, we can save up to 10 to 40% power. In particular, depending on the specific phase of the mission. So LEOP is one mission, is one part of the mission where we are saving the most of it. And this power saving can also then be converted into mass saving. So if you're consuming less, perhaps you can reduce the size of the battery. How we want to prove our technology, we have, this is kind of the roadmap. We have 2 approaches. One is more on our on-ground testing, so more conventional. And another one is going to an orbit as soon as possible via in-orbit demonstration, in-orbit validation. On the on-ground testing, we are perform quite significant amount of tests. So in phase 1 and phase 2, we mainly focus on the thermal side of the of the testing. So we perform thermal suckling, thermal vacuum, vibrational heavy ion. And then in phase 2, we start focusing on the top coating. So a radiator have to be able also not only to emit the infrared, but also to reflect the visible light. And this is quite a challenge for us because anything that you put on top of our radiator have to be infrared transparent. So we spend a lot of time in trying to optimizing this top coating. And in order to prove that the coating is actually able to withstand the harsh environment of space, we had to perform atomic oxygen, UVA, UVB, and so on. Now we are in, we started, I think 6 months ago, a collaboration with Visa and Airbus. Is a GSTP project that is aiming to push the TRL to 6. This is these are the sample actually that next week we are sending to Airbus and that we will test it in their facilities. On the in-orbit demonstration and in-orbit validation, we perform in 2023 a stratosphere mission, so it's not really an IOD. And in 2025, we are working on the 4 mission. 2 are already in orbit. They are 1.5 picosat. And then soon we're going to launch a 3U and another 2P. In 2026, we are targeting an even larger platform. So we are hoping to sign a contract soon for a microsat size platform. And in 2025, in 2027, a minisat. These are the main mission that we are targeting, but also we are also looking for a smaller mission, which can help us to develop our technology forward. This is some image that we got for our mission 1. Okay, this is a stratosphere mission. Was quite exciting mission to do because it was the first time we integrated our payload into a CubeSat size platform. And it was great for marketing because we were able to get this beautiful picture of our device working basically as an infrared display. So we were able to write SmartIR in space using watching with an infrared camera. Payload mass was 2 kilo, 50 watt power. The duration was only 2 hours, so it was quite a small mission. But we really learned a lot. And then the fact that we were able to retrieve the payload really helped us to understand what got wrong and what can be improved. Mission 2, this is actually an IOD that we perform in collaboration with Alba Orbital, Hydraspace, and Amsat AE. This was on Transport 12. The deployer was Alba. That was the Alba pod. The duration of the mission is 1.5 years, so it's quite a long time to test our material in space. And the payload that we produced, it was extremely light, so we were allowed only 35 grams, so we had to really shrink down all our electronics and our radiator. The payload power was 0.5 watts, so extremely low. And we were able to radiate between 0.5 to 1 watt, depending on the state of the radiator. We have two radiators. One is facing the space, that is the white one here. And then we have also an internal radiator here, that is basically more act as a contingency plan. And then we had the possibility to test 2 of this top coating that I mentioned before. So we have some sensor underneath, and we can see how the space is degrading over time, this coating. The mission was a success, and it still is. So the satellite is and the payload are healthy and operational. So after 2 months, which is very exciting. There is no sign of degradation so far on the coating that we developed. The optical performance, we were able to determine it in space, so we were able to measure alpha and epsilon, and we were able to prove the radiator performance, both passive and very recently active. Of course, we had some challenges. We had some set of sensors that didn't behave as they should, But luckily, it's just in the right condition, they are still operating. So this is was a big learning process for us. This is some of the data that we are gathering. So we have temperature sensor, visible light. This is the payload power consumption. And then this is the infrared sensor that I talk about. Mission 2.1 is another contingency mission. So it's the same payload that we launched for mission 2. Now it's currently in orbit, but has not been deployed by the orbit. So we are really waiting for it. This was a video, but it doesn't work. Yes, this is me holding the satellite, and this was the scary moment of the integration during in the clean room of Alba. Mission 3 is more ambitious. So this is like a collaboration with C-Shark. This is a 3U satellite. I'm not going to go much in detail on this platform because they're going to split it, I think, tomorrow. But the payload size is significantly big. So we're talking about half kilo. Payload power is about 10 watt. Radiated power that we can radiate is between 7 to 14 watts. So it starts to be quite significant. And we have all sorts of sensors. We have over 100 sensors. And what we're planning to implement is a visible camera and an infrared camera as well. Here, I had a question, what is the best way to transmit a photo? I think I will go and ask you around about it. But also, another exciting bit is that we can perform a lot of testing, material testing on this platform. Last mission that we are doing this year is a 2P picosat, and this I wrote IOD IOV because this is going to be a commercial platform that C-Shark is planning to launch. It's launching a constellation and the idea here was how we can increase the performance of the solar panel or the deployable solar panel. And one way is to add our smart radiator at the back of the deployable solar panel in order to decrease the temperature of the solar panel. We are currently working on this mission. It's still not yet finalized our payload, but we are quite excited to see how it's going to perform. In conclusion, yes, in 2025 we'll be launching 4 satellites. We are looking for partner in 2026 and 2027. And if you need a radiator to improve your satellite efficiency, please come and talk with me. Thank you.